Hi, welcome back to Math 111 lecture. Today we're going to finish out Chapter 2 with a conversation about regression. Now, regression is a fancy word for curve fit. What this means is we can take sets of data, points that we have measured or found, and we can find a curve that best fits those points. So let's look at an example. We're going to look at this in Desmos. And if you want to, I'm going to show you how to do regression on Desmos because it's quick and easy and pretty intuitive. If you want to know how to do it on your calculator, I will show you that in class. Or if you can't make it to class, then please make an appointment with me and we will do it via web conference. All right, so in order to explain this, let's work with a sample data set. And we're going to have 2 points, 1, 2, 3, 1, and 4, 3. We somehow found these points. And what we want to do is we're trying to find the curve that is somehow close to these data points. So I'm actually going to go to Desmos really simple. And I've built this already, but I'm going to show you how to do it in a minute. So what I've got are my 3 points. We have got my points 1, 2, 3, 1, and 4, 3. Those are the green dots on my graph. Now, straight lines are nice. We like to fit lots of things to straight lines. So we're going to start by saying, well, maybe I can do this with this straight line. And what we're trying to do is you can see that I'm adjusting my slope. I can adjust it up and down. And what I'm trying to do is find the line that is equally close to all of the points. And what I mean by that is, you see the right? So you can see that none of the points are actually on line. But there's some distance from which each point is separated from the line. That's what we call the error. And in a minute, I'm going to turn on the Desmos version of this. What we want to do is we want to minimize this distance. And we do this with something called least squares regression. And there's a whole statistical process for doing this. But essentially what we do is we take the distance between the point and the line, and we square that. And we do it for each point, and then we find the line that results in the smallest sum of all of those squared errors. And if I let Desmos do it, Desmos will find the line that minimizes that error. Now, this data set is not very linear, but all you do to do this is, so it doesn't look very good, but this is the line that best fits all 3 of these data points. Now, let's look at how to actually build this thing with some actual data. So there's an example in your book, example 2.5.1. It's on page 226 of your text. And what we're looking at is some energy consumption data in different years. And this, we're going to talk about a couple of things when it comes to data points and time. We can do it this way. Okay. So let's just start with a new graph. So I'm going to just make myself a new blank graph now. Some things you probably have not done yet with Desmos that Desmos can do. See this little plus up here? Desmos allows you to add different things. Expressions, notes, tables, folders, even images. We're just going to add a table. So if you looked on page 226, down close to the bottom of the page, there's a table that says year and energy usage in quads. Now, quads are quadrillion BTUs. So, but all we're going to do is just type in that data. So 1950, year 1950. we used 34.6 quadrillion BTU of energy. 1960, that increased to 45.1. 1970, 67.8. And you see none of these are showing up on my graph. That's just because I gotta zoom way out. There they are. They're right here. Okay. 1980. We use 78.3 quads. 1990, 84.6. 2000, 98.9. Okay. If we plot that, we kind of need to zoom into this region right here in order to make it make any sense. So you can see a couple of problems already. My data is grouped between 1950 and 2000, which means I'm only using up 50 units of this great big giant excess. There are a couple ways to handle it. We could just leave it alone, or right, we'll try just leaving it alone. Does it look linear? Let's blow this up. Yeah, it looks like we might be able to put a straight line through there. So let's see. Let's check it out. Here's what we do. We can add an expression. And what we're going to do is we're going to type y1. And I just typed y and then 1. And then tilde. And this is the little squiggly guy you sometimes see over N's in Mexican or in Spanish writing or other languages, right? And then M. That tells Desmos we're thinking this, so then we're going to put an x1 and then put in plus b. And Desmos gave us a line. Not only that, Desmos gave us the equation for that line. See it right here? Gives me slope and y-intercept. So how do we tell if this is a good fit? Well, what we do is we look at, you see this r squared right here? This guy? This guy right over here in statistics on the left. If it's close to 1, it's a good fit. That's the way the model's set up. So, yeah, that's a pretty good fit. The other thing we can do, if we zoom out a little bit and we let plasma, so you see this E1? These would be errors. Remember I talked about the distance of that separation between the points in the line? If it's a good fit, these errors should all be kind of scattered around the origin. And you know, these are pretty good. And yeah, that's pretty good. There's some above, there's some below. Good fit. We can take those off with Control Z or undo up here. So that's how we do, that's the basis of linear regression. Linear regression just says fit a straight line to the data. We know it's linear because we said linear. It's going to make a straight line. Not all data sets are going to fit a straight line. Let's look at another example of a set of data that does not fit a straight line. Oh wait, let's see if there's a question we can answer. So can we predict the energy consumption in 2013? Yeah, we can. How can we do that? Well, point on the line, right? So we want point 2013, that's our x-coordinate. And then to get to our y, we just take m times our x, which is 2013, plus b. Notice I typed that expression right in the coordinate point. And if I want to see what that number is, you can click on it. And Desmos, sorry, I have bugs. Desmos tells me it's 117.128 quadrillion BTUs. Our growing population and our growing reliance on electronics are costing us. Okay, that's the basis of linear regression. Let's look at a different data set, and let's talk about whether or not it's linear and what to do with these. So again, I'm going to start with a new blank graph. I'm going to start by putting my data in a table. And I'm on page 228 of your textbook. We're looking at the National Weather Service data for time of day versus temperature in Painesville on March 3rd of 2009. So at 10 o'clock, it was 17 degrees. At 11 o'clock, it was 19 degrees. At 12 o'clock, it was 21 degrees. Now, the next time point is 1 o'clock. But if I put in 1 o'clock, Desmos isn't going to know that I mean 1 in the afternoon. So I got to use military time. So I'll use 13. This is like hours after midnight. 14 for 2 o'clock, 15 for 3 o'clock, 16 for 4 o'clock. And if I graph those, and again, I have to, if the Desmos has graphed them for me, I just have to find them. There they are. Oh, that doesn't look very linear. And I can see that that's not going to work. If I put in a linear model, yeah, that's not very good. That's not very good at all, is it? What's it kind of look like? Almost looks like part of a parabola, doesn't it? Let's try a parabola. Let's try this. Let's turn the sky off. And let's try y1. And the tilde is what tells Desmos it's going to be doing some work. And we can just type in ax squared plus bx plus c. Maybe. Oh, can't. All right, you know what? I will spend time between now and when we get together in person figuring out how to do this with a non-linear model. I know it is possible, but I am not going to waste our time on this video doing that. What I want you to do is make sure you understand what we are doing when we do regression. I want you to understand that when we do a regression, we are looking at the best fit model. So we're creating an equation that will represent our data points. And we are minimizing the error between our equation, which predicts a curve that will represent our data and our actual data. So we're not going to hit every point, but we can get pretty close. And let's talk about why we would want to do this. So, because if we understand how to do stuff like this, we can do things like put a Donald Duck sketch up and then make our computer draw Donald Duck. So this is a computer sketch of Donald Duck based on a whole bunch of linear equations, a whole bunch of equations. Each one of these little line segments is represented by an equation on the left-hand side over here. Another example of why we want to do this. Here we have a boat on the water. And again, this is all built with equations. As we understand how equations work, we can build things like this. And because this is Desmos, there's some animated stuff. We can put a beach ball on. Let's see, there's the beach ball. Okay? So notice the waves are actually moving. There is a beach ball right here. Beach ball and the umbrella. All right. I'll quit torturing you. Until I see you again, have a great time doing math. Worked on these regressions a little bit. You can certainly do a linear one. And I will.